Ring flipping in cyclohexane happens millions of times or infinite number of times every minute or every second. We'll see what it is and how it's happening and what are the changes happening in the molecule during ring flipping. Now we can say that ring flipping is the interconversion of conformations. Particularly when the cyclohexane ring flips, it converts from one chair conformation to another chair conformation. Now here you can see this chair conformation and the second chair conformation, they are almost like mirror images of each other. And this particular arrow mark, this is the arrow mark which is used to designate flipping. Okay, so this you have to understand the different. We have different arrow marks in organic chemistry, and this particular arrow mark with the equilibrium arrow mark and reversible arrow mark over which you have two hemispheres. Okay, so that's the arrow mark for ring flipping. Now coming back to ring flipping. Now we said that one chair conformation flips to form another chair conformation. That is, earlier this carbon was the top on above the plane, and if we number the carbon atoms, let us number it 1, 2, 3, 4, 5, 6. Now carbon 1 was above the plane, carbon 4 was below the plane. When it flips, carbon 1 goes below the plane and carbon 4 becomes above the plane. Alright, so now we can say that whichever carbon atoms were above the plane goes below the plane, and whichever were below the plane goes above the plane during ring flipping. And this doesn't happen immediately at a stretch, that is one chair to another chair. It passes through various other conformations. That is, for this chair to flip into this chair conformation, it has to go through various other conformations. Like we know that our half chair form, twist boat form, etc. Well, I'll just show you the diagrammatic representations. So if you have the chair conformation here, okay, it first gets converted to the half chair conformation. So what's happening? The carbon 1 is kept, is remaining above the plane. Carbon 4 has come to the plane, or it has come, is on the plane now. Okay, now twist both carbon 4 and carbon 1 and carbon 4 are above the plane. Okay, and the other carbon atoms also have, there is also a change in their position from the plane. What happens next is you get a boat conformation, okay, then twist boat again, then half chair. The second half chair, if you see, in the second half chair, the carbon 4 is above the plane and carbon 1 has gone into the plane. Okay, and in the next chair conformation, carbon 1 has gone below the plane. So it happens like this. Now it passes through all these conformations: half chair, twist boat, again twist boat, again half chair, and then finally to the chair conformation. Now, what we must remember is that it has to pass through these conformations for flipping. It doesn't happen. Carbon 1 and carbon 4 does not change the planes simultaneously. If that happens at a particular instant, both these carbon atoms, that is carbon 1 and carbon 4, will be on the plane. That means we get a planar cyclohexane. Now that's not possible, energetically not possible. That is the reason why one chair conformation flips to another chair conformation via all these other conformations. Okay, to be more, if we need more, we'll look at this in three-dimensional manner at the moment. Remember, this flipping happens throughout. Wherever you have a cyclohexane ring, this flipping happens. Alright, now we'll see one video from, with the help of ChemTube 3D, how the flipping happens. To understand the ring flipping using three-dimensional model, I am taking the help of ChemTube 3D, the usual website which I refer to get the 3D models. Now this is the chair conformation of cyclohexane. Now we shall try to flip this. Now remember, ring flipping doesn't mean rotating this in this manner. Okay, this is just rotation of the molecule or spinning the molecule. Ring flipping means we are going to flip this, that is, we will be shifting this, or the bonds will be flipped to bottom and to the top side. We'll see that. Now here we have the chair conformation. Let us see what is happening during the ring flipping. You can see here, just observe. See, slowly the bond is moving. You can, if we number the carbon atoms 1, 2, 3, 4, you observe carbon 1 and carbon 4. Carbon 1 has come down. Okay. And now you can see slowly carbon 4 is coming up. And we have arrived at the opposite, or the mirror image of the first first chair conformation. Now, so during ring flipping, carbon 1, which was above the plane, goes below the plane, and carbon 4, which was below the plane, goes above the plane. Now, next what we need to observe is what's happening to the the orientation of the substituent bonds, or the CH bonds on this. Okay, now we'll see that once more. We'll just see. See, now this is the earlier position. We had carbon 1, 2, 3, carbon 4. Now this is the carbon 1 axial bond, CH bond, and this is the carbon 1 equatorial CH bond. Now when a ring flipping happens, you just concentrate on the axial CH bond on carbon 1. It has taken the equatorial position. Right? I'm sorry, I cannot get the if it was colored, it would have been easy for you to understand, but then hope this is clear to you. Okay, so the during ring flipping, all the axial CH bond gets converted to equatorial CH bond, and all the equatorial CH bond gets converted to axial CH bond. Now you can observe the CH bond on carbon 4, or the equatorial bond on carbon 1. Now we have the equatorial, this is the equatorial bond on carbon 1. Okay, you just keep an eye on the equatorial bond on carbon 1. See what's happening during ring flipping. So the equatorial bond has become the axial bond. Okay. Of course, their position has, they have become, they're gone below the plane, but it has become the axial bond. Okay, so equatorial has become axial, and axial has become equatorial. Now that is one change which is happening in the, during the ring flipping. Hope it's been clear to you. You can watch other videos also wherein colored images are used. I cannot use those images because they are not mine. Alright, so in YouTube you get lots of videos. Go through those and try to understand. Now, looking at the video, what we find is when ring flips, carbon 1 has come down, carbon 2 has come up, carbon 3 has come down, carbon 4 has come up, carbon 5 has come down, carbon 6 has come up. So those carbon atoms which were above the plane has come down, and those which were below the plane has come up. So here 1, 5 and 3 were above the plane, now it has come below 1, 3 and 5. And 2, 6 and 4 were below the plane, now it has come up 2, 6 and 4. Okay, so that's a change which is happening while ring flipping. Now we'll see one more picture for more clarification. Here you can see I have marked this axial bond over here. Okay, now this is one chair conformation wherein you have an axial bond and an equatorial bond. Now it's passing through the various conformations for flipping: the half chair, the twist boat, the boat, again half chair, and now here you see what's happened. The axial bond has now come to the equatorial position, has taken up the equatorial orientation, and the equatorial bond has taken up the axial orientation. So during flipping, this happens. During flipping, all the axial bonds present on the cyclohexane will be oriented in the equatorial position, and all the equatorial bonds will be oriented in the axial position. Okay, you would have seen it in that video. Alright, now this particular concept, that is, when we have in our earlier video we have said that those bonds which are parallel to the C3 axis, they are called axial. So all those bonds gets converted to the equatorial. Okay, and the equatorial bonds will become parallel to the C3 axis. At the same time, we had mentioned about alpha bond and beta bond. Those bonds which are above the plane, or which are pointing above the plane, are called beta bonds, and those which are pointing below the plane are called alpha bond. Now you see here this axial bond on chair A becomes equatorial bond on chair F, but it is still alpha. Okay, it is still alpha, it is pointing below the plane. And the equatorial bond on A and the axial bond on F, it is still beta, it is still above the plane. Okay, so during ring flipping, the axial bonds orient to the equatorial position, but the alpha beta bond doesn't change. Whichever was an alpha, or whichever bond were alpha, will remain as alpha. Okay, so that you must remember. Now let's see once more the picture of the changes happening. See, we have the one chair conformation. When it flips to the other chair conformation, we of course get a mirror image, but you see all the black axial bonds has been oriented in the equatorial position, and the all pink equatorial bonds has been oriented in the axial position. So that's a very important aspect in ring flipping, the change in the orientation of the CH bonds on cyclohexane. Now this passes through the boat conformation mainly. Okay, and in boat you can see while passing through the boat conformation, most of the axial bond has taken up the equatorial orientation. See the axial bond on 4, 5, 3. This side has become equatorial, and the equatorial has become axial. In the next cycle, all these will change their orientation. Now, when the energy of these conformations were analyzed, they could have come up with the energy profile diagram, which shows like this. That is, the chair conformation is having the lowest energy and half chair conformation is having the maximum energy. So we can say chair conformation is the most stable conformation in cyclohexane. We did see a few reasons why chair is more stable than boat in the last video. You can go back to that video and check it out. Now you see here the energy difference between the chair, boat and twist. Particularly the boat and twist is so low that we cannot separate them. Okay, separation of these conformations are not possible at room temperature, not possible. And at room temperature, there is so much of interconversion, or almost 1 million interconversions happening every second, as I said earlier. And always, almost 99% of the molecule exists in the chair form. Okay, so that's the most stable conformation. Okay, so chair is the most stable, half chair is the least stable, and you can say the order of stability: chair, twist boat, boat, half chair. Okay, that is the order of stability: chair, twist boat, boat, half chair. Alright, so and the energy difference between chair and half chair is 10.5 kilocalories per mole, while the energy difference between boat, twist boat and chair is very low. Okay, the difference in energy is very low. Alright, and remember, almost 99% of the cyclohexane ring exists in the chair conformation. So these are the points related to ring flipping. And the next class we shall see what is the what makes the these different conformations energetically different. Alright, hope it was clear to you. Thank you.